So, last lecture we associated to any ideal class in an imaginary quadratic field a positive definite binary quadratic form with discriminant equal to the discriminant of this field. Okay. And the association, it depended on choice of z basis of this ideal. But if you modify the if you choose a different z basis, you get an equivalent binary quadratic form. And so, what we proved is we associated an equivalence class of binary quadratic forms to any non-zero ideal in an imaginary quadratic field. Today we will see what happens if you choose an equivalent non-zero ideal in an imaginary quadratic field. So, let me recall what we did last time and then start with the new topic today. So, A is contained in OK, K over Q is imaginary quadratic field. So, you fix a z basis and we had a further restriction at some point, which was that imaginary part of alpha 2 by alpha 1 is bigger than 0, right. So, if that is not true, then all we have to do is take a change the order. So, if imaginary part of alpha 2 by alpha 1 is less than 0, then this will mean that imaginary part of alpha 1 by alpha 2 will be bigger than 0. Okay. And imaginary part can't be 0, because this will mean that alpha 1 and alpha 2 are linearly dependent over real numbers, but K is an imaginary quadratic field. So, when you so two elements of K that are linearly independent over Z will also be linearly independent over R. Okay. So, that of course is not true for a real quadratic field. Okay. Alright. So, what did we do? We wrote any alpha in A as x alpha 1 plus y alpha 2, and then you take norm of alpha. This is this is of the form So, anyway, what I will write down directly what we had. So, if we take something like this will be of the form x squared plus bxy plus cy squared. Okay. So, this is the binary quadratic form that is associated with A and the choice of basis alpha 1 alpha 2, and if you choose a different basis, you get an equivalent binary quadratic form. Okay. So, today what happens when so let us say you take a different ideal, which is beta times A for some non-zero beta in K cross, right. So, this means that A prime and A are equivalent ideals, okay, equivalent ideals. This means that A prime and A define the same class in the ideal class group CL of K, right. So, what happens then? Well, I will tell you that you actually get the same binary quadratic form, not just equivalent, and the reason is the following. Well, as long as you fix a basis. So, fix a basis alpha 1 alpha 2 of A, then beta alpha 1 and beta alpha 2 is a Z basis of A prime, right. Recall that A prime was beta times A. Okay. So, if you fix a basis alpha 1 alpha 2 of A, then you get a basis beta alpha 1 beta alpha 2 of A prime. So, if alpha prime belongs to A prime, then alpha prime is equal to beta times alpha for some alpha in A, and so you can write alpha prime, right. And so if you write alpha as x alpha 1 plus y alpha 2, then alpha prime is beta x alpha 1 plus beta y alpha 2, and then norm of alpha prime divided by norm of A prime squared. What is this? This thing is simply norm of beta times alpha prime, sorry, beta times alpha divided by norm of A prime squared, right. Okay, and right. So, a norm is multiplicative. So, you get norm of beta times norm of alpha divided by yeah. So, at the bottom you would get something like norm of beta squared times norm of A squared, right. Okay, just give me a second. Okay, so okay, maybe this is not how I want to write it. Let me redo this. So, if I look at norm of beta x alpha 1 plus beta y alpha 2, then this thing is simply right. Okay. So, x squared times beta alpha 1 multiplied by sigma beta alpha 1. Recall that Galois group of k over q is 1 and sigma, right, plus xy times beta alpha 1 sigma beta alpha 2 plus beta alpha 2 sigma beta alpha 1 plus y squared times beta alpha 2 sigma beta alpha 2, and if you write this out, then this becomes norm of beta norm of alpha times x squared plus here again you get norm of beta times xy times alpha 1 sigma alpha 2 plus alpha 2 sigma alpha 1, right, plus norm of beta times y squared times norm of alpha 2. Okay. All right. So, yeah, and so if you divide out by norm of beta, sorry, this should be alpha prime, norm of beta, you get norm of alpha, right. Okay. So, yeah, there is some error I am making here. Yeah, okay. Yeah, fine. Okay, so the error I was making is yeah, you do not have to, sorry, this is an error I made and I hope I did not make it in the previous lecture, is you do not have to divide by norm of a square, you have to just divide by norm of a, right. That is the error I was making, because a, b and c are not divisible by norm of a square, they are only divisible by norm of a, and so this is an error here and an error here as well, right. Okay. So, I can then divide by norm of a. So, I get norm of alpha prime divided by norm of beta times norm of a. This is equal to norm of alpha divided by norm of a, but norm of beta times norm of beta times norm of a is simply norm of beta times a, which is norm of a prime. Okay. Hence, we get the same, hence binary quadratic form associated with a and a prime are the same, right, once we fix a basis after fixing basis of a. Okay. All right. So, and then we know that if we change basis, we only change by an equivalent form. Also remark is we had this condition on the ordering of the basis. So, if imaginary part of alpha 2 by alpha 1 is bigger than 0, then imaginary part of beta alpha 2 by beta alpha 1 is also bigger than 0, because they are the same number, right. Beta is a non-zero element of K. All right. So, what have we done now? So, we have associated equivalence class of binary quadratic form to every element in the ideal class group of K. Okay. Right. So, what we have done is, we have taken a map from this to binary quadratic forms of discriminant dk and then modulo the equivalence relation. Okay. And the claim is that this is a bijection, okay, which means that this map, this function is 1 to 1 and onto. Okay. So, why is this 1 to 1 and why is it onto? One way to prove that a function is 1 to 1 and onto is to just define its inverse function, right. So, we define inverse of this map, inverse function as below. Okay. So, what do we need to do? We need to start with a binary quadratic form in an equivalence class and get an ideal class out of it, right. So, how do we do that? So, let a x square plus b x y plus c y square be a binary quadratic form of discriminant dk, okay, that is kind of important. So, dk is b square minus 4ac. Then we can write this thing as follows. So, we can take a common out of it and we can write it as x plus lambda times y and x plus sigma lambda times y, right. And we know what this x and y, what this lambda and sigma lambda are, right. So, so you take a common out of it, you get x squared plus b by a x y plus c by a y squared, right, and we know how to factorize this. So, so the roots of this are minus b by a plus minus square root of b square. Yeah, sorry, what am I doing? That is not what I wanted to say. I want to say that the roots are roots of ax square plus bxy plus cy square equal to 0 are yeah. So, x by y equal to minus b plus minus square root of b square minus 4ac by 2a, right. So, one of them will be lambda, the other one will be sigma lambda, right. So, you can take lambda to be minus plus square root of b square minus 4ac by 2a, and then sigma lambda is simply the conjugate of that, right, complex conjugate of that. Okay. So, I have now implicitly fixed a orientation of this lambda, so that imaginary part of lambda is bigger than 1. Okay. All right. So, so again doing what I wrote on the last page, this thing is equal to a times x plus lambda y and x plus sigma lambda y. Okay. Or maybe I should actually write minus then. Yeah, okay. Maybe I should write minuses here, and then yeah, okay. Still imaginary part of, yeah, maybe then I should do the following. Okay, now everything is fine. Okay, so so I can take the ideal, x plus lambda y inside lambda inside z right, inside not z, I want to say okay. Yeah, I think I have still made slight error about what lambda is. Okay, let me actually erase this, whatever lambda is, I do not care, but yeah, right. The roots are this, so that is kind of clear, and I choose, so choose lambda such that imaginary part of lambda is bigger than 0. Okay. All right. So, you take these this ideal x and y in z, right. So, this is an ideal inside OK, right. Yeah, take this ideal, sorry, not the other one, take this ideal inside OK. So, this has z basis given by a and a times lambda. Okay. And you see now that this agrees with our choice of basis as before, because alpha 1 is a and alpha 2 is a times lambda. So, alpha 2 by alpha 1 is lambda whose imaginary part is bigger than 1. Okay. All right. So, this is how we attach an ideal to a binary quadratic form of discriminant dk. Okay. So, starting with a binary quadratic form, you get an ideal like this. Now, we need to show that if you take equivalent binary quadratic form, we get the same ideal class, right. So, we need to show that equivalent binary quadratic form gives same ideal class. Okay. And how do we do this? Well, there are two ways to rectify this. One is you just associate a ideal to reduced binary quadratic form of given discriminant. Then there is a unique one in each class and you do not really have to worry too much, but that is kind of a that is not an ideal way to do things. You it is better to say that if you take a equivalent binary quadratic form, you get an equivalent ideal inside this. And well, how do we do that? So it is kind of cumbersome to write the whole thing down, but let me try anyway. Right. So remember, an equivalent binary quadratic form will be given by a matrix like this, which will have the following relationship P Q R S, and then A B by 2, B by 2, C P R Q S. And so if I multiply everything out, I get A P plus B by 2 Q, B by 2 P plus C Q, A R plus B by 2 S, B by 2 R plus C S, P Q R S. So this is AP squared plus BPQ plus CQ square, and then similarly here we will have A R square plus BRS plus CS squared, and then here you would have APR plus B by 2 QR plus PS plus CQS, and then the same kind of thing here, A PR plus B by 2 QR plus PS plus C QS, right. It has to be, the non-diagonal entries have to be the same. They are both B prime by 2 anyway. So that's all fine. What does that mean? That means that A prime is A P square plus B PQ plus CQ square. Did I get that right? Yeah. Right, and then C prime is whatever it is, etc., etc., right. So right, and so B prime is 2 times A P R plus B by 2 P R plus Q R plus P S, Q R plus P S, Q R plus P S plus C Q S, right. Okay, and then C prime is A R square plus B R S plus C S square. Okay, right, and so if I write A prime x squared plus B prime x y plus C prime y squared, then this I want to write as A into x plus lambda prime y and x plus sigma lambda prime y, right. And so all these things are then written in terms of A prime, right. So, what is lambda prime then? Yeah, so this is where I should have calculated lambda prime. Right, so yeah, so lambda prime, I think what I had written was right in the, and then I got rid of it. But anyway, so lambda prime is minus b prime plus square root of b prime. Yeah, maybe minus here because I want the minus lambda to have. Oh, okay. So lambda to have this sign. Yeah, minus lambda was the right thing, I guess, right. So b prime square minus 4 a prime c prime, but by 2 a prime, but you see that this b prime square, so the discriminant is the same. So this does not change, I can replace this by square root of dk. So b square minus 4 ac is same as b prime square minus 4 a prime c prime. So this is some calculation that we had done before, right, and yeah, and so b prime is whatever it is, right. Okay, so so you can check. Let me leave that as an exercise, that the ideal generated by A and A lambda is equivalent to the ideal generated by A prime and A prime lambda prime, right. I mean, you get rid of this A prime in the denominator anyway, and then there is some calculation to do to find a scalar which works for you. Okay. All right. So and then you also have to check that this is the inverse of the function that we defined earlier, meaning that when you start with this ideal, you get back your binary quadratic form that you started with, but that is kind of easy because you just need to take norms of all the elements and they will be given by this binary quadratic form. So there is some checking to do which I am not doing for you, but it is good to do this checking and to get familiar with this. Okay. All right. So what we did today was prove that there is a bijection between binary quadratic forms of a given discriminant up to equivalence and ideal class group of the field of the same discriminant. Okay. And in the next lecture, we are going to use this to compute some ideal class groups of imaginary quadratic fields. Thank you.